In this video, I'm going to discuss briefly about the assumptions of one-way ANOVA. Okay, so the first and very important assumption is the population from which the samples are obtained must be normally or approximately normally distributed. If not, then the sample size must be big. What do you mean by big sample size? So each of the sample must be bigger than 30. Okay. So to test the normality of the sample, you can normality of each population. So you can use Shapiro-Wilk test for each of the sample data, or you can use the Shapiro-Wilk test for the residuals. Okay, or QQ plot for the residuals. That will do for all those populations. So residual. So Shapiro test for the residual will test the normality for all populations. Okay. So what is the residual? Residual is basically the error. What is the error? Error is the difference of the data from its column mean, right? That is the error or the residuals. So difference of the data or the deviation from the data from the column means, from each data from its column means. Okay. Next is the sample size are roughly equal, meaning that all the samples must have almost equal sample size. So that means that usually the largest sample size of the largest sample divided by size of the smallest sample should not exceed 1.5. So less than 1.5 or equals to 1.5. Next one is the sample must be independent of one another. What does that mean? That means no influence of one sample on the another sample. Okay. So probability of picking an object or a subject in the sample does not impact the probability of picking the object in the another sample. Okay. Next one is the variance of the populations must be equal or almost equal. So the variations among the population must be equal. That can be tested by using Levine Test, Flinger Test, or Variance Test, but also can be viewed graphically by plotting the residuals versus the fitted. Okay. And the sample must be simple random sample. So all other except the first one and then the fourth one, okay, can be just see the data, and then you can and then see how the data is collected, and then you can decide whether that assumptions are validated or not. But for the normality of the population and the homogeneity of the variance, that is the variance are equal, we need to use the statistical test or graphical techniques. Okay, so let me do the same example I was doing, that is the pigs weight for different diets, right? So let me run that. So I'm using that directly. So from R. Now for the test of assumptions, what I'm doing, the first one is the homogeneity of the variance. Okay, I'm using the graphical method for this. What you do is you do the plot result 1. What is the result 1? Result 1 is the name of that ANOVA test, result of that ANOVA test. Okay, so what you do is plot and result 1, comma 1. If you do that, then it shows you see that these are the residuals value for each of those columns. We had 4 columns, right? And for each of those columns, these are the residual values, meaning the deviation, the difference of the data points on that column from the column mean, and then you plot that. See, that is 0. That dotted line is the actually average of these residuals. You see that average of these residuals are almost the equal, right? And also you see that they are almost equally scattered, right? Their variances are also equal. You can see that. But sometimes you see that this red line is increasing or decreasing. In that case, the homogeneity of variance is violated. As long as the red line is close to the dotted line, then homogeneity of variance is satisfied. Okay, now this is just the graphical way, but if you want to do the statistical way, so the first one I'm doing is a Levine test. This tests the homogeneity of variance for more than one samples. Okay, what we got here is 0.7205. This is the p-value. Okay, so the p-value is 0.72, which is greater than alpha, meaning that the null hypothesis was the variance are equal, alternative are variance are not equal, hence the variance are equal, right? So that's what the p-value greater than alpha. We do not reject the null hypothesis. Another is the Flinger Test. Okay, Flinger Test is useful when population are slightly departed from the normality too. So let's look at that. We got also p-value is greater than alpha, so the variance are equal. That is the homogeneity of variance. Next one is the test of normality. The straightforward way is plot. Result 1 is basically the name of the result from the ANOVA. Okay, you do that. If you do this, this is the normality plot of the residuals. Okay, standardized residuals here. So this is the normality plot, and it sounds like they are normal, right? But there are some of the data they are away from that line. But if you want to do the Shapiro test for the residuals, okay, Shapiro test for the residuals, if you do that, you get p-value is 0.07, which is greater than alpha. Again, alpha is 0.05. Hence, the populations are approximately normally distributed. Okay, so in the lab 9 file, you can see another example done manually and as well as done using R, where I have tested the assumption. So in example 2, there is one thing that you see that, so I am using one way dot test. This is another way that you can apply for the analysis of variance. You can apply to test the equality of the population mean in different populations. Okay, so so you see that, so I have also done one more test. There is a Bartlett test for the homogeneity of variance. You can apply Bartlett's test as well. All right. So, and I have done the test of normality and test of homogeneity of variance. So this one is the by the way, did I do the, yeah, test of homogeneity of variance is here, and I have done that. Okay, guys, so you can look at that example yourself. Exactly the same steps, exactly the similar problems. So in the next video, I will show you how do I do the analysis of variance or the ANOVA if the variance between the populations are not equal. Okay, thank you.